Okay, so let's get continued. So in today's class, we're just going to have two simple concept I want to introduce. So the first concept is on thermal stress. Now, when I talk about thermal stress, I always like to discuss example. I'm sure everybody has experience. So imagine if you have a soda can, right? A can of soda that hasn't been opened, and then we all have the experience. If you leave that in the fridge overnight, what's going to happen? The soda is going to pop, right, by itself. Because the reason is because the soda internally usually is in liquid state, right? Just like water. So liquid state, the density is around 1 gram per cc, right? Now, once you lower the temperature, delta T becomes lower, right? So it frees up, right? So the density of this is, let's just do H2O, and this is ice. I shouldn't say H2O because ice is also H2O, water, ice. Ice becomes less density, so 0.9 grams per cc. Now, I did not add any of soda into it at all, right? So M stays the same. In other words, volume equal to mass divided by density, right? So if the density decrease from water to ice decrease, right? Chances are mass stays the same, then your volume has to increase, right? So when the volume increases, the internal force or internal stress gets high, so therefore it's popped, right? That's popped. So that's how it's determined. Oh, another thing is we also know, like pretty much for all the metals, it has thermal expansion, right? Once you heat a metal up, it becomes larger. If you cool it down, it becomes smaller. So this is also very easy to understand. Usually the metal, if you look very closely, using optical microscope or even using electrical microscope, you see the atoms, right? The atoms, the distance between it, once the temperature goes up, the distance becomes larger, all right? Now the distance between the atoms, if the temperature goes down, the distance becomes smaller. Of course, the volume will be increasing if you heat up, and the volume will decrease when you cool it down, okay? Now, here's the thing. If this metal is encasted on a fixed frame, in other words, if any of these edge of the metal cannot move, it's fixed in a box, in other words, this metal, okay? Then of course, when you heat it or when you cool it, especially when heating up, it wants to expand, right? But it cannot. So therefore, there's lots of internal stress being developed. Make sense, right? So therefore, in this section, we want to show you how this temperature can also induce internal stress. Okay? All right. So in order to quantify these temperature-induced stress, we have an equation to summarize it. Now the equation, let me just mention it for now. So we say for most of the time, the expansion or contraction delta T is T stands for temperature, okay? Is linearly related to the temperature increase or decrease delta T that occurs. Okay, so in other words, using an engineering equation to summarize it, so delta T is displacement of the thermal expansion or shrinkage equal to alpha delta T times L. Okay, so let me give you a brief introduction. What is alpha delta T and L? So this alpha is the most important parameter for thermal expansion. That is called linear coefficient of thermal expansion. Okay, Now, it is just like Young's modulus or Poisson's ratio. It is property of materials. All right, so it's within the materials property by itself, so you cannot really change it, right? So the unit is 1 over Fahrenheit or 1 over degree C. Or sometimes when we do scientific experiment, we like to use Kelvin, right? So Kelvin, 0 Kelvin means absolutely 0, which is minus 276 or something like that. I forgot the exact value. Okay, so the reason why it's 1 over, I'll explain that to you later, right? So this delta T is nothing but temperature change. Temperature change. Okay, temperature change, we know temperature can either go up or go down, right? So delta T can be either positive or negative. For example, if it changes from 100 to 200 degrees C, then delta T equals to 200 minus 100, that is 100 degrees C. You always use end temperature to minus the beginning temperature, okay? Now, if it changes from 100 to 0 degrees C, then delta T is 0 minus 100, which is minus 100 degrees C, okay? So you can see delta T can be either positive or negative, all right? Okay, so this L over here is the length of the member. So we call that, for example, a ball, we call that a member, right? And of course, this is the original length, okay? All right. Now, this delta T is change in length of the member. Okay. All right. Now, let me summarize this thing a little for you. Delta T equals to alpha delta T times L. Now, sometimes people also like to write it in the other way. I'll show you. Delta T over L equal to alpha times delta T. So what is delta T over L? Displacement over original length. What's that? Yeah, that's strain, right? Thermal induced strain equals to alpha times delta T. Okay. Now, alpha usually it's always a positive number. Okay, it's very small. That tells you it's very similar like strain equal to 1 over Young's modulus times stress, right? Remember, stress equal to Young's modulus times strain, right? Just write it the other way. So positive stress will give you positive strain. So the higher stress means higher strain, right? Same thing here. Now, if delta T is positive, that tells you delta T chances are it's positive as well because this alpha is always a positive number, okay? That's for most of the case. For example, metal, if you heat it up, you're going to see expansion. If you cool it down, you're going to see a shrinkage. So positive temperature change give you positive strain, right? But there's a special case, like the water, the example I just gave you in the beginning of the class. When you put the soda in the fridge, delta T is what? Negative, right? Because you change that from room temperature all the way to maybe minus 20 degrees C. But the strain induced is positive because it expands, right? Because the water becomes ice, the density becomes higher. It's because there's a phase transformation involved, all right? So once you have phase transformation involved, things are different because the density and everything, they're different, okay? So this water has a special case, which we'll deal with that later. Chances are we're not going to deal with that in this class because most of the stuff we're studying, as you can see so far, is aluminum, stainless steel, plastic, right? They're all solid. So we're not dealing with phase transformation yet, okay? So don't worry about it. In other words, positive temperature change always give you expansion, and a negative temperature change, which is cooling, always give shrinkage, okay? All right, so let's see how we can deal with that. So it's a very simple concept, so I'll probably just give you one example, and then we should call that good, okay? So let's look at this example here. So we have there's a brass rod, so a copper alloy, all right, AB, and also aluminum rod BC. They all joined, welded, for example, right? Joined it at the collar B and fixed, connected at their ends. So just like those conditions we learned in last class, both ends are fixed in the wall, okay? Of course, I'll draw you a figure. Now, if there is no load in the member, right? So there's no extra loading in the member, all right? But when T1 equals to 50 degree F, a little bit lower than room temperature, determine the average normal stress in each member. When T2 equals to 120 Fahrenheit. Okay, also, how far will the collar be displaced? So basically, how far the collar will be displaced. Okay, and the condition also give you is the cross-sectional area of each member is 1.75 inch. Oh, no, cross-section area has to be inch square, so let's just use inch square here, okay? Okay, one more condition give you is the brass has a 14.6 MSI, megapascal per square inch for Young's modulus, okay? And the alpha brass is 9.8 times 10 to the minus 6 per degree F. Okay, E, aluminum is 10.6, what's going on, 10.6 MSI. Alpha aluminum is equal to 12.8 times 10 to the minus 6 per degree Fahrenheit. Oh, so one thing I promised to introduce to you, explain to you, which I didn't, is this. So epsilon t equals to alpha times delta t. Remember, that's the equation we use to determine the thermal induced strain, right? So tell me, what is the units for delta t? Okay, so in other words, delta t, of course, is degree C, right? 500 degrees C minus 200 degrees C is 2 degrees C. Now this alpha, in other words, is thermal strain divided by, yes. What is the unit for strain? Unitless, right? There's no unit at all. So what is the unit for delta t? Like we mentioned, delta C. So therefore, the unit for alpha is nothing but just 1 over degree C, okay? So because it's unitless over degree C. Now sometimes people like to write in this way, degree C inverse, right? They're the same thing, as you can see, okay? All right, so let's see this problem. The drawing looks like that. So there's two sections, and then there's two different materials. So they're connected together, and then they are fixed on both ends, right? So this is one material. Let's use orange. Well, there's another one. Let's use blue. So they are two different things. Okay, they have different material properties. There's section A, section B, section C. Okay, so the total length from AB is 3 feet long and BC is 2 feet long. Alright, and of course with these Young's modulus, AB is brass, that's why I use a copper color, and then aluminum is BC, so therefore make sure you use the material property correctly. Okay, so let's do this. This is a aluminum, so it's all blue, and for brass everything is all like orange color. Okay, all right, so there's no stress or force applied. The only thing is you have a temperature change, and we know temperature induced strain, right? So be careful. Let's see how we can solve for that. Okay, now let's do a free body diagram, of course. Okay, so let's see here. There's a section right in the middle. There's another section. Okay, thermal expansion. Now here we have no external force whatsoever, right? The only thing we have is you'll have a certain expansion and a certain contraction, and then you have a total displacement. Now we also know delta AC is 0 because A and C are both fixed, right? So therefore the total AC displacement has to be 0. Okay. Alrighty, so let's see what we can do to solve for it. Alright, so two sections, brass and aluminum. Okay, BR and AL. Okay, so let's look at it here. So this force over here, we have summation F has to be 0, right? So therefore the internal force of the brass and the internal force of the aluminum has to be the same. Why is that? Because overall there's no force whatsoever, and you can imagine this is just one type of a force, right? So the internal force in the brass and the internal force of the aluminum, they have to be equal because there's no extra load whatsoever. Make sense? Okay. Alrighty. So therefore, another thing we can do is coupled with that. Okay. So two conditions give us. Okay. So let's see here. Now delta AC is 0. There's something interesting. So chances are this is our equation 1 already. And equation 2, we have FBR times L. That's section AB. That's brass section. And AB times EBR. Now, don't forget that this is displacement caused by internal force because of the thermal expansion, right? What else do you have? We have alpha brass times delta T times LAB, right? This is what we just learned. This is thermally induced displacement, okay? So this total is the displacement of AB. Not only you have the internal thermal expansion force that can cause displacement, but in the same time, you have a thermal induced strain. Make sense? Now, this FBR is not 0. Why? Because AC is fixed. When you heat it up, you have internal force. Okay? Alright. This is all AB. Plus whatever the BC is, right? So let's assume over here the displacement of AB has to equal to BC. Now, let's assume AB is just positive. Doesn't matter, okay? Now, BC, the displacement, has to be negative. Remember, we did it in 2 days ago, right? One of them, the two springs, right, connected together. Okay, so both are fixed. You have a force going that way. Now this is induced internally. Now one of the spring has to be positive, the other spring has to be negative. Same thing here, right? When you have a heat expansion, maybe one of the material will expand more than the other. Of course, the other will be undergoing compression, right? So let's do that, and this is FAL times LBC divided by ABC, then times EAL plus is alpha AL delta T times L of BC. Okay, all right, so this is what's happening. This is all the displacement caused in BC. Okay, so one of them is positive, the other one is negative. I don't know which one's which, and I don't care because it doesn't matter, right? Okay, so plug stuff in, okay? So here, let's see, FBR, that's something we don't know, but we know FBR and FAL is internal force, so they're the same, okay? Internal force, they're exactly the same, and the diameter are the same, by the way, okay? So FBR is nothing but F, and LAB is 3 feet long. I want to transfer that to inch. Why? Because remember, the Young's modulus is MSI, pound per square inch. So we want to use inch, okay? So therefore we can cancel a lot of things. So 1 foot equal to 12 inch, right? Divided by 1.75 times times 10 to the 6, because that is a the Young's modulus of it. Oh, I think I got that number wrong. Let me do this. 1.75 is a cross-section area, 1.75 inch square. That's a cross-section area for both AB and BC, alright? Inch square. Okay, so that's inch square. Perfect. Multiply by 14.6 mega, which is 10 to the 6, okay? PSI, mega PSI, MPSI, or MSI for short. That plus this thermal expansion, 9.8 times 10 to the minus 6 times 120 minus 50. So, and the temperature, initial temperature, right? That's my delta T. And again, 3 times 12. 3 feet times 12 inch. Okay. Now, let's do a little discussion. Here, I didn't mention what is the direction of these displacement, right? So chances are, as you can see, of course, when you have temperature increase, this will be positive. It wants to expand, right? Now, these two things add together, it has to equal to the other, right? The other half, which is BC. Now, chances are this internal force, guess what? It has to be negative. Why? Just think about this. You have a section that's fixed, then you heat it up. It has nowhere to go. Of course, you want to expand, but cannot. So therefore, this reaction force will give you a compression force. So it wants to compress it, right? So therefore, it does not expand. Make sense? Then that's something be careful, right? So we have to at least know this is positive displacement caused by thermal expansion, but chances are this part will be negative. Okay, let's deal with that later. Doesn't matter for now. Okay, so that AB section has to equal to BC. So let's do that. BC has F times 2 times 12, and then 1.75 again. 10.6 is that's aluminum. 10 to the 6 plus I have 12.8 times 10 to the minus 6 times again 120 minus 50, and then again 2 times 12, okay, 2 feet. Alright, so this big equation is something we can use. Why? The only thing unknown is F. Notice that? Yeah, so okay. Using your knowledge on the force and F, that just equal to a internal force, and like I mentioned, it's negative, right? So therefore, If you leave the negative sign, that's fine, but if you don't, it's okay too, because we need to calculate stress. We don't really care whether it's tensile or compressive stress. The only unless we care is the stress. Okay, so let's just take the positive number here, 17 point. Sorry, let me just not use kilo. Let me just 7093.4 pound of force. Okay, use your calculator, you'll find it. Okay, so but still keep in mind this is compressive. Okay, doesn't really matter here for now. Okay, so next is we need to calculate the stress, right? Determine the average normal stress. Stress is nothing but force divided by cross-sectional area. Force is the same for both brass and aluminum, and then the cross-sectional area are the same, 1.75. So plug your number in. That is your answer. Inch square, pound per inch square, PSI. Okay, 9.77 KSI. Okay, already. And then so another thing is this let's see here. So another thing we want to know is how far will the collar be displaced. Okay, so the amount of the collar will be displaced means, you see, these two are connected together by this collar, right? AB and BC. So this color, if I use a orange to highlight that, or using a red to highlight that, so if AB expand and the BC shrink, then of course this color will be pushed towards the right direction, right? Now, if BC expands a lot but AB compress, then chances are this collar will be pushed to the left. So therefore, this collar has to have some displacement, right? So the next thing is let's quantify how we can quantify the displacement of B. So delta B, let me not use red. It's not that important. Delta B is nothing but, remember, we can have internal force 17 O. Let me just use the negative over here. 17093.4 times 3 feet. Just use the equation we learned 2 weeks ago. Okay, 1.75 times 14.6 times 10 to the 6 plus 9.8 times 10 to the minus 6 times 120 minus 50 times 3 times 12. That's 3 feet. So whatever over here, I just cannot fix. Fit into that. But anyway, these two are one piece. All right. Okay. So honestly, be careful. This is negative force, like I mentioned, because simple expansion, right? So it causes internal force, and then that's compressive. Okay, so delta B, let's calculate that out. That is nothing but I used FL divided by AE plus alpha delta T times L. Okay, so nothing fancy, but I'm sure you already know, but just in case, I write it here. Okay, so then plug your number in is 0.611 times 10 to the minus 3 inch. Okay, very, very small, some milli-inch. Okay, so that is my answer. That means this delta B will be pushed towards the right a little. Okay, so this is how it's calculated because it's still positive number, and of course you can imagine AB is longer than BC, right? So therefore it gets pushed to the right. So that's displacement of the collar. Okay, very simple. And another thing I found out is actually the video is very, very large in a size, almost 1 gigapascal. So I cannot record a